Alors, خصني نحيد هاد التكست دغيا دغيا. Ok. Salam alaikum كلشي. D'abord, on va faire une deuxième. C'est pas une deuxième, c'est une énième conférence à l'AI. Où اليوم on a un invité qu'on a déjà invité avant, compétition Think AI اللي دارت il y a quelques mois, Maha Elbayad, اللي هي research scientist في Meta. Donc avant de commencer, juste une petite précision. On a eu quelques messages privés, même des followers de la page qui disent que pourquoi est-ce qu'on fait des webinars de AI et pas d'autres choses, des trucs plus élémentaires de maths. En fait, c'est... bien sûr, notre cible, c'est pas forcément les gens qui aiment que l'AI. Notre cible, c'est les Marocains en général, en particulier Nas, les qui aiment le maths. Ou donc, je préfère préciser, on est en train de discuter en interne, des conférences pour un public plus large, des notions élémentaires de la maths pour attirer les gens envers de la matière. Donc, voilà, donc Maha. Salam Maha, merci d'être ici. Donc, je vais pas trop prendre de temps entre les parce qu'on est serré par le temps. Je serai sur les coulisses, donc si tu as besoin de quelque chose, laisse-moi know. Ou bien sûr, tu peux faire la présentation en anglais, arabe, en français, donc peu importe. Voilà, yallah, bon courage.
Merci. Du coup, salam alaikum. Donc la présentation, je vais la faire en anglais. So I'm here today to talk about Seamless M40, which is an all-in-one massively multilingual and multimodal machine translation. So this work was released in August this year, so like a month ago, and it's like a huge team effort aiming at building translation model not only for text. So when you think Google Translate, you're thinking translation of text, but I mean even Google Translate has speech too. But this is like an effort to make one single model that can handle both text and speech. So for a little bit context, or I guess more on the context of this project. So the project is called Seamless, hence the Seamless M40. So the goal of the whole project is to enable communication without language barriers. I don't know if you attended any of my previous talks with Morocco AI, where I presented the NLB, No Language Left Behind, which was like also a massively multilingual machine translation model, but only for text. So I guess in terms of progression over time, we started with text, we started with scaling the number of languages with text, and we released NLB 200 that supports 200 languages. Most of them are low resource languages, so languages for which you don't have enough data on the internet that you can use to train your models. And the next natural extension for our project was to include speech. Because a lot of languages in the world are not written. So if you count like the whole 7,000 languages, only 3,000 of them are written. And even the written ones don't have a standardized writing system. Like if you think, for example, Moroccan Arabic, some people write it in Arabic script, some people write it in Latin script. Even within the Latin script, you have multiple versions or variety of the same word. So there's no like standard way of writing these languages. So the next extension, as I mentioned, is let's include speech. It's more practical, accessible, and it sort of removes all of these writing system barriers that make it difficult to train multilingual, or I guess massively multilingual translation models. So before the release of Seamless M40, most of the existing models, if you want to translate speech into text, let's say I speak in French and then the output text will be in Arabic. So that's speech-to-text translation. And there's also speech-to-speech translation, which is I'll speak in French and you'll hear my voice translated into Arabic, for example, in voice. So it's either speech on the input side and speech on the output side, or speech in the input side and then text on the output side. The existing systems are what we call cascaded systems. That's not specific to translation. Cascaded system is idea of putting multiple systems in a pipeline in order to solve a particular task. So for the case of speech-to-text translation, you will start with ASR, which is automatic speech recognition. So you will transcribe whatever I'm saying. And then once you have whatever I'm saying in text form, then you can run a text-to-text translation model to convert it to another language. So for speech-to-speech, it's even more complicated. So you have to stack multiple systems. So you start with ASR, transcribing my speech into text, and then text-to-text translation again. And then after that, you have to synthesize that text into speech with the TTS model. So there are a lot of issues with this kind of techniques, like cascading systems. The major one is error propagation. So if you have an error in system one, then there's no way of system two to get a correct output. Same if you have one, two, three, then any error from one and two will sort of propagate to the downstream models, and the output is more it's highly probable to have a faulty output of these kind of systems. And they're not trained jointly, so you have a lot of domain mismatch. Let's say you have an ASR system trained on, let's say, Wikipedia, someone reading books, for example. So it's strong in the domain of books. And then you have a text-to-text translation model that is trained more on like scientific texts. Though, because of this domain mismatch, your models will not be able to perform the downstream task properly because they're not aligned to begin with. So the other options is direct systems. So I don't know if you've heard of Whisper or Valley or Audio Palms, and those are models that can do speech to text translation directly without going through the proxy of, or I guess the pivots of ASR, like transcribing the speech first. And these models have other issues as well. They're not massively multilingual, especially in the case of Valley, whereas Whisper, for example, can support 82 languages. AudioPalm also a few hundred languages, but most of them are not massively multilingual. And the massively multilingual ones, such as Whisper and AudioPalm, do not evaluate on all the languages they support. So I don't know if you've read any papers in the space of speech translation. Usually they will claim, we support 1,000 languages, but when you read the paper, you find that they evaluated only 5, French, German, and Spanish, or something like that. So they don't evaluate on all of the languages. And for me, like as a researcher, I don't sort of take that for granted that you can support 1,000 languages if you do not evaluate properly on some benchmark that supports all of these languages that you claim to support. And the third point, I guess, is that, the main one is that they don't compare to cascaded models. So the standard, like the gold standard, if you want the best quality translation, is to use cascaded models. And these direct systems will always behind the cascaded models. So what we want with the seamless in 40 is a multitask, multimodal MT model. Here, MT usually, if you're in the space of NLP, whenever you hear MT, you're thinking text translation, but MT stands for machine translation. So there's no way. Why not include other modalities in the name of MT? So in our case, we're considering MT as translation, regardless of the modality. It could be speech or text, and our goal is to train a model that can do all of these 5 tasks. First one is automatic speech recognition. I give you a speech, you transcribe whatever I'm saying, which is a conversion from speech to text. And then speech to speech translation, so speech in language A, and then output speech in language B. And then text to text, similarly, language A, language B, but the modality is text. And you can, think of any combination of these, modalities on the input side and modalities on the output side, and the model should be able to perform any task that takes either speech or text and output either speech or text. So in terms of language coverage, we're covering 100 languages on the speech inputs, 96 languages on the text inputs and outputs, and then on the speech outputs, 35 languages that are supported by the model. So in our team, as I mentioned, it's a huge multidisciplinary team, and all of the efforts, or at least the contribution, as we wrote them in the paper released in August, are centered around 3 axes. So the first one is data. I don't know if you attended any AI talk, the first, I guess, item in the agenda is like what data is used to train this model. So here we use a lot of data, either human labeled or pseudo labeled, but the contribution of our model is also using automatically aligned data for speech. This is what we call mining. So we usually have a lot of data on the internet, but it's not aligned, so you don't have pairs of, let's say, speech in language A aligned with text in language B. So you need to create this data by yourself. The second aspect is modeling. So here it's what I described earlier. So how to create this multitasking, multimodal model that can do all of these translation between either speech and text into either speech and text. And the third axis is evaluation. So as I mentioned, I have a lot of complaints about how these models are evaluated, and we came up with different methods of how to evaluate properly these methods, on the side of multilinguality, but also on the side of robustness, how fair they are, how responsible they are as AI tools. So I'll start first with data. Although I don't work on the data aspects of this project, so most of my work is on the modeling side of it, but I'll just give you a brief sort of description of our data efforts in Seamless Info. So again, if you've seen any of my talks about NLP, the key idea is the same. So we need a space in which speech and text are mapping to the same space. So like if two sentences are, for example, here I have only text monolingually. So I love eating and I enjoyed food a lot. Those sentences have the same meaning, the same semantics. So they are in that space close together. Whereas sentences with different meanings will be mapped, or I guess mapped in that space very far apart. So this is the key property we want in a space. So I encode any of these sentences, and depending on their proximity in that space, I can like pick a sentence, and the closest one in that space will likely be a paraphrase of that sentence. So this is in the case of monolingual space. We can make this space also multilingual. For example, I have the sentence, I want to call you, and أريد الاتصال بك. So they are in the same space. They have the same meaning, albeit in two different languages, but they will be mapped to the same point in space, more or less. And then we'll have this true for not just multilingual text, but also for speech. So I have here the symbols for audio. Ideally, we want any audio that carries the same meaning, like someone saying, le chien est brun, it will be also in the same space, or I guess in the same neighborhood as that embedded of the sentence carrying the same meaning. So this is a semantic by design. So this is a space that is semantic by design. So we'll only care about the semantics of the speech. If I'm saying, for example, the same sentence, but now I'm whispering, it should be ideally in the same point. So it will sort of remove or move away all of the characteristics of the speech and focus only on the semantics. So how do we achieve, or I guess how do we train encoders that will map to that shared space multimodally? So the first approach that we presented in NLP was what we call laser. So you have first an encoder for one language, that is the teacher, and then you teach students per language family or per language if you want, but you push them to be similar. So you have aligned data. I have the sentence in Arabic, I have the sentence in French. I will encode them and I will just minimize the cosine distance between these two embeddings. It's basic, but it requires a little bit of parallel data in these multiple languages so that your student model will learn to map to a similar spot as the teacher model for a different language. By extension, now we have it for speech too. The only difference now is not you have speech encoders as students, and similarly you can minimize the distance. In laser, we found that the cosine distance worked best. Here we minimize the mean square error between embeddings of either text and speech, and then we also train a decoder similar to laser just to ensure that whatever embedding is learned is useful for decoding and learning like a meaningful sentence at the end. So the core idea of it is that we want a shared space. So now I have laser encoder, which is for text. I have a German speech student that is also learned by the technique I described to map to the same space, and then maybe another German text student this time. So for each modality, for each language, or for each language family, you will have a set of encoders, but the goal of them is that they all map to the same space. And now I can leverage this space to mine my pairs for training. So how we do this? So again, similar to NLP, there's a lot of similarity with what we did for text. They just extended it to speech. You will have segmented text here. So the top part we have text in multiple languages. We have Arabic, English, and Vietnamese, for example. And then we have also audio in the same languages or a different set of languages. And then we will embed each of them separately using whatever appropriate encoder we have that maps to the sonar space. And once we have this space now containing all of our samples mapped in the same sonar space, then we can just mine whichever is the closest. Let's say I pick a sentence in Arabic, and I'll pick all the closest points to that input that I have to find pairs that are what we call here speech-to-text aligned data or speech-to-speech aligned data. So most of these data will be not properly proper translations. They're not human-generated translations. They're just aligned, but it's a good enough approximation sometimes. And you can filter this data based on the similarity scores. So as I mentioned, we're optimizing either cosine distance or L2 distance, and we can sort of sort all of the potential translation of a given input and then pick whichever, I guess, at some threshold, this is enough, or I guess good quality data, and then beyond this threshold, it's going to be useless data. So all of these data now that we gathered with this process of mining will be used to train the seamless M4T model. So in terms of modeling, I want to start first with some key concepts that are not part of the project per se, but they're existing techniques since 2019, at least, the discrete units that we use heavily in our work. So with discrete units for speech, I don't know if you're familiar with sequence-to-sequence models. So if you have any experience in NLP, you know that sequence-to-sequence models are sort of the key architecture used to learn a lot of AI models in the space of NLP, and to sort of learn a general model that will map from one space to another, sequential data in the input space and then two sequential data in the output space. So here it's similar, except speech is not really a discrete sequence that we can use the sequence-to-sequence models on. So we need to discretize or quantize the speech. So how do we do that? Or I guess a lot of people did before us, is to take speech inputs. So here, for example, let's say we have a corpus of, 400 hours of speech. So you select a few samples, you'll encode them with an encoder, and then you'll pick some layer in that encoder, and now you have this continuous representation of speech, but you still need to discretize them. So you'll take these continuous representations, apply some clustering techniques. The main one we apply is k-means, and now we have k-centroids. So these k-centroids will represent, or I guess will be used to represent any speech inputs. So in practice, we'll have our speech inputs. We'll have intermediate features from a speech encoder. Here I have example with a Hubert, XLSR, with Wegbert. Regardless of what speech encoder you have, you just pick one representation, either the final one or ideally some intermediate representation. And now you have these continuous vectors that represent your speech inputs. Given the k-centroids that you found or learned in the previous steps, you will just now cluster these multiple vectors, and instead of having these xt vectors or t vectors, x1 up to xt, you will represent them by just the centroids associated with each one of them. So now this is a discrete representation of speech, and any sequence, or I guess any input audio, will be presented as a sequence of centroids. And now we have a limited vocabulary depending on how many centroids I chose when I was running k-means. So in our case, we use 10,000. So that means any speech audio input will be written as a sequence of tokens, or think of it as words, from this vocabulary of k elements or k vectors. The second thing that we use for our speech encoder is a conformer. I'm guessing everyone is already aware, or I guess familiar with transformer, but conformer is a sort of an upgrade of transformer in the case of speech. So the only difference here, if you're familiar with transformer, is there is another additional feed-forward network that is sort of sandwiching the multi-head self-attention. It's called like a macaron-like architecture. So we have two feed-forward networks, and on top of the multi-headed self-attention that is characteristic of transformer models, there's another convolutional module that is added on top of that. So it's a transformer model with some additional convolutional layer and maybe the structure of the macaron feed-forward network. But other than that, you can think of it as a transformer model. So the architecture that we use in our model is called multitask unity. So I will just describe the whole flow of the architecture, and most of these components you should already be familiar with, either, for example, conformer because I described it now, or transformer because everyone knows transformer at this point. So we have, in our case, either speech inputs or text inputs. So if I have a text input, I will send it to a transformer text encoder. If I have a speech input, I will send it to the conformer I described just now. And this conformer is also usually followed by a linked adapter, which is a basic convolutional layer that downsample the input. Because the major issue when you move from text to speech, like text, maybe it's a sentence of 30 words, whereas speech, if you take, for example, as I described with discrete units, so you have these multiple chunks of 20 milliseconds. If you have a long audio, you end up with a very, very long sequence. So we resort to something like a simple downsampling to sort of reduce the length of this sequence and just maybe reduce the memory usage of these models. So this is now we have encoded our speech or encoded our text. So we have either speech features or text features, and we'll just simply decode them with a text decoder. So the text decoder will output text corresponding to whatever input I fed. And these tasks, we call them X2T because it's ASR, text-to-text translation, or speech-to-text translation. So any task that takes X, whatever modality that is, speech or text, and output texts. So now that we have our text output, then we're already covering this set of tasks, but we're also interested in generating speech. So to generate speech, we'll take these features from the text decoder and then move them, or I guess convert them into units with another transformer text-to-unit decoder. So I guess the key idea of transformer, or I guess any sequence-to-sequence model, is just you have a sequence of input and a sequence of output. So in the first stage, we either can have text and text, but here we use something similar, except that the input sequence is text and the output sequence is unit. Basically, it's a converter from unit to units, and now we're converting text to units. Once we have our units generated by the unit decoder, then we can send them to what we call a vocoder. Here we use the hi-fi GAN vocoder to sort of convert these units back to the speech in the shape of a waveform. So in general, what you call multitask unity, or I guess, as I mentioned earlier, there are cascaded systems, but there are also direct systems. And usually when I describe this model, like a lot of people say, this is not really direct, it's cascaded, which is sort of true for at least for the part with generating speech, except that a lot of definitions keep changing of what is a direct model. In this case, a direct model, or I guess an end-to-end model, is if you have even these components that are sort of, they look like a pipeline of different components. Ultimately, you're training all of this jointly on some parallel data. So we have parallel data of speech to speech. So we can train the whole pipeline on some data, I guess in a supervised way. And similarly, we can train speech to text or text to text. So we have data that we can use to train all of these components jointly, excluding the hi-fi GAN vocoder that is, in our case, trained separately, and it's considered sort of outside of what we call the multitask unity model. So now that you know sort of what is the outline of a multitask unity model, the question is of how to train all of these model, all of the components of this model. As I mentioned, we jointly fine-tune the components at some point, but like a lot of them are already sort of pre-trained separately. So the four components that are pre-trained separately are the seamless M40-NLB, which is a simple text-to-text machine translation model. The second component is our speech encoder. So it's a wave-to-vec BERT2, and I will explain later why it's called 2.0. And then the TTU, so the converter from text to units, and then vocoder, which is the converter from units to speech waveforms. Where was I? All right. So the first component is wave-to-vec BERT 2.0. I don't know if you're familiar with wave-to-vec BERT, but it's a method to train SSL model, like self-supervised models, on speech and labeled speech. So you have this, let's say, have 1 million hours of speech, and you want your model to learn some useful representation from this data. This is unlabeled data. You don't have speech aligned with text, you just have speech, and you learn some representation similar to how BERT, for example, is trained on text-only data, or GPT is trained on text-only data, or any language model is trained on text-only data. This is sort of the equivalent of that for speech, except that it's only for encoding, so it doesn't generate speech as much as you can learn representations, and then you can take this representation and maybe either translate them or just run some classification on top of these features. So our model is trained on 1 million hours of speech, and this 1 million hours free of speech is usually crawled from the internet. So you don't know what language is in each chunk of audio, but we you can run some LID model, like a language identification model, on this data, and we identified at least 143 languages. Again, there's no guarantee that this is exactly 143 languages, but the goal here is just to learn a speech encoder that is multilingual by virtue of looking at data from different languages. So the only difference between wave-to-vec BERT and the 2.0 version that we use in Seamless M40 is we use additional code books when training this model. I'm not going into details of how wave-to-vec BERT, the initial one, is trained, but usually you have these speech features, and similar to what I described in discrete units, you have these code books that will quantize your continuous representation from your conformal speech encoder, and now you can just use those as tokens and mask some of them and predict whatever is masked. So quite similar to BERT. The only additional step here is that you need this quantization because you don't have discrete data, you have continuous representation. So you just add that quantization part, and then the rest is similar to BERT. So the second component is Seamless M40 NLB. Again, it's a text-to-text translation model. You have a lot of by text data, either back translated or human translated or mined as well. And this is like similar to what we did in NLB, just use the same data, except that now this project is only 100 languages. So we trained a much smaller model, 1.3 billion versus 50 billion in NLB. And this one is trained only on the 96 languages, which is a subset of the 100 languages that is written. The rest are not written at all, so don't have a text part, I guess text component for these languages. So again, similar, it's a basic transformer dense model that translates from one language to another language with a transformer sequence-to-sequence model. So now that we have the two components that I described, we have a speech encoder, which is a conformal speech encoder with its length adapter trained via the wave-to-vec BERT algorithm, and we have the text encoder decoder from Seamless M40 NLB. So now we want not to do text-to-text, but we want to do speech-to-text. And for that, we have our speech to, I guess, align data between speech and text. In our case, because we're doing X2G, we use triplets of data. So we have X on the source language and audio, and then the same audio now in text form. So you have your input in both text and speech form, and then your output in text. So you have now these triplets. So given these triplets, you can train or optimize three losses. I guess two key ones, which is the speech to text cross entropy. So basically, you're just optimizing the maximizing the log likelihood of observing the text output given the speech inputs, and you do similarly for the X for the source text to the target text. So you maximize the log likelihood of observing the target text given the source text. And now we can also add an additional loss, which is the knowledge distillation between these two. So given that this blue blocks, the transformer text to text, are already pre-trained, so the text decoder is already familiar with how to decode text, but for it, the I guess reading speech is a new task. So for that, we use the text to text as a teacher model. And then the speech to text is now the student learning from the text to text model by just minimizing the Kullback-Leibler divergence between the probability of predicting the text given the input text, and then the probability of predicting the text given the source in speech form. So in terms of amount of data we use to train our X2T model, so I mentioned, I described a little bit the mine data, but in terms of like how much that constitute in all of the data we use to train the X2T model, it's, I would say, approximately 7 to 8% of our data is mined. So most of the other data is ASR data. And then we take this ASR data and we do what is called pseudo-labeling. So ASR data, you have the speech in French associated with the text in French, and you also have it in multilingual. You have also the speech in English associated with this text in English, and so on and so forth, but it's not the same speech. So you can take this ASR data, let's say French to French, and you can take that French text, translate it with some text-to-text translation model. In our case, we use our previous NLP models, and we translate this French now to Moroccan Arabic or Chinese, whatever other language, and now we have speech-to-text translation data. It's not human-generated, it's model-generated, but it helps us a lot to train our model to perform this new task of speech to text, for which we don't have that much data compared to text translation. So in terms of amount of hours, it varies from language to language. I guess similar to text too, we had, like, for example, English, you'll have million and 100 millions of bytext, like text aligned from one language to another language. But once you move to some low resource language, like for example Yoruba in the set of African languages, or even Moroccan Arabic, for example, you find very less data available to you. So in this case, pseudo labeling helps a little bit. And because the data is imbalanced, we have to resort to some sampling of these languages to sort of balance them out. So we will downsample the highest resource languages, like for example in this graph that will be Chinese and Japanese, and when upsample the low resource languages to sort of catch up and sort of prohibit the model from forgetting altogether about the low resource languages, because it will see the high resource languages much more without this downsampling. So now that we know how to generate text and we have our X2T model that can generate text, the next part is like, how can I generate speech now? So I mentioned the TTU, and we pre-trained this TTU too. It's trained on ASR data, because the TTU doesn't translate, it just converts a sequence from text to units. It will be in the same language. So in the example here, I have the English sentence and then the English corresponding sequence in terms of units. So this model is trained on ASR data, or I guess technically it's TTS data, but it's like ASR data in reverse. So ASR is like speech to text, it's in the same language. TTS is text to speech, but if you have data for one, you can have it for the other. So here it's trained on TTS data, and then and also combined with ASR data. And then we do also use this model for pseudo labeling. So I described the whole process of how to get speech to text data. Some of it's human translated, some of it mined, some of it's pseudo labeled. Now we add an additional step of pseudo labeling. So you have speech to text. Now you take the text and also convert it to units with this TTU. Now you have speech aligned with units, and now you can train your model to sort of directly predict speech, or guess units from speech. So we have two versions of this model. One is bigger than the other, and the bigger one we use for pseudo labeling as a sort of a teacher TTU, and then the smaller one we use to initialize the architecture I described earlier, the multitask unity. It's much smaller, but for our purposes, it's it helps reduce the memory footprint of the model, but also it will learn from the bigger model that is used for pseudo labeling. So it seems like a sort of a trade-off between the cost of running inference and the cost of training versus the cost of the quality of the generated units. This last component in generating speech is the hi-fi GAN vocoder. So as I described, we have these discrete units, and our discrete units come from the 35th layer of XLSR1B. Again, these sort of details are empirically decided. You try with different models, you try with different layers. This one tends to generate the better units, but there's no like proven recipe of why this one is better. I mean, you could argue like depending on where it is in the architecture. Like if you go deeper, maybe the units will be more abstract and will not capture like what we want, which is sort of word level representation of the speech. And if you go very, very early in the architecture, then the model will be maybe focusing too much on half a phoneme, and not even a word. So you should sort of strike a balance between what granularity of speech you want based on what layer you choose from the architecture. We use 10K audio samples from our data. So I mentioned earlier, like you have to train or I guess run the k-mean clustering algorithm and come up with the sets of vocabulary that is used to encode speech. In our case, we have to sample audio samples, I guess sample some audios, and you cannot run this on the whole available, like we have 1 million hour of audios. It's not feasible to do that on a 1 million hour of audio, so you downsample your data set, or just pick from multiple languages. You try to balance again which languages are used when sampling these audios, and then you just encode them as I described with the k-means algorithm, and then clustering into 10K centroids. We trained this vocoder again. So if you read previous work describing the hi-fi GAN vocoder, usually it's monolingual, so it's not a multilingual model by design. But to make it multilingual, we sort of add an additional auxiliary loss in the training of the hi-fi GAN unit vocoder, which is a language identification loss. So we want our model to sort of not merge all languages together. So we want it to still be able to distinguish a language from another, because sometimes when you train multilingual models, you tend, for example, to generate something that is sort of a mush or a mix of languages instead of just, the language that you have in your input. For example, here I want English, but I want my audio to be English. I don't want it to be mix between English and Spanish, for example. So if you're interested in the hi-fi GAN vocoder, there's like the paper on hi-fi GAN vocoder, and also another work that we published prior to Seamless in 40 that makes this hi-fi GAN multilingual. So yeah, the last stage that we have now, this additional purple and green components, the TTU and the vocoder, is to train on speech-to-speech data, as I described how to get it, with pseudo labeling and binding and so on. And now we freeze the X2T component of this architecture and then fine-tune the rest. So basically, we're encouraging the TTU to align with the X2T model that we trained in the first stage. And then once we have that, then we have a good model that can take speech as input and generate all the way at the end of the TTU units, and then send them to the vocoder for synthesis. In terms of data, we have much less data in speech to speech compared to speech to text. Because ASR data is already much more than you have in speech to text, and then we add pseudo labeling on top of that, so we have much more speech to text data than speech to speech. And again, similar issues. You have a lot of imbalance. For example, here we have a lot more data in French and German and Spanish, the high resource languages, and much less on the other languages. So we try to add more mined data to those languages and add more pseudo labeling to those other languages. So in terms of results, as I started with the comparison to cascade model and complaints of why cascaded model are still the go-to choice if you want speech-to-text translation. So here we compare to these cascaded models. And usually also when you read papers comparing to cascaded models, you have to sort of manufacture a baseline that is, I guess, good for your work. So, for example, if you're training a small direct model, you're not compared to the strongest component out there in terms of cascaded models. Whereas here we pick the best ASR model out there, which is Whisper. So we have two versions of Whisper. So Whisper Medium or Whisper Large V2, which is like the state of the art in ASR, in English, but also in multilingual data sets, or I guess in multilingual setup. And then we combine that with NLP, which is also the strongest translation, like text-to-text translation model that we can find. And we pick again two sizes. So we can I guess combine these different models to come up with like a equally sized models, but that's not a constraint. We can also include cascaded models that are much larger than our models, but then just the comparison will be we outperform models that are much bigger, or we just outperform models that are the same size as ours. So these are our models, the seamless in40 medium and the seamless in40 large. So one has 1 billion parameters, the other is 2 billion parameters. There are no way close to what you hear when you describing the size of large language models. So here is like 2 billion is already like a large model in the space of translation. So the other two direct systems that we compare against are Whisper Large. Again, Whisper can do both ASR and speech-to-text translation, but only into English. So ASR it does for multilingual, or I guess in multiple languages, and then for speech-to-text translation, it can only take multilingual speech and translate into English. So that's why here I only evaluate on X to English, but not English to X, which is like English source to non-English target language. Same for Audio Palm. Again, they also claim that we can do into non-English languages, but they're never evaluated into non-English languages, despite the fact that this data set that I evaluate on, which is FLIRS, already exists. So Exo English, we are outperforming Whisper by more than 24%. So the metric here is blue, because you're comparing your generated text into the reference text, and usually when you're comparing text to text translation, even in without the speech components, you use blue, which compares n-grams. If you're not familiar with the blue, basically looking at n-grams of the text and trying to measure some precision based on different sizes of n-grams. So here we outperform Whisper by 34%, AudioPalm by 22%, and most interestingly, we outperform the largest cascaded model, which is the Whisper Large V2 plus NLP 3.3 billion model, by 6%. I mean, you can call it at parity, but it's still improvement compared to X to English cascaded models. On English to X, the story is a little bit less, I guess, positive compared to X to English. So compared to cascaded model, if we compare to the equally sized cascaded model, we are on par with that. So that would be the 21.5 versus 21, for example, which is the cascaded model that has 2.8 billion parameters. But if you take cascaded model much larger, then your model, or I guess these cascaded models, will outperform Seamless in 40. So we are still 3% behind the best cascaded models. So in my sort of interpretation of this, usually when you're translating into different languages on the target side, you need your decoder to be much bigger because of the sort of competition between languages on the target side. So as I mentioned, sometimes if you're training a small decoder and you're training on, you say, dialects from Arabic, then usually if it's small decoder, then you end up with outputs that are a mix of all of these dialects. Whereas if you have a much bigger model, they're sort of splitting the model parameters, and you will have quality translation in each of these languages separately. So here again, we're always outperformed by the NLB 3.3 billion, which has a much larger decoder, but we are on par with the equally sized decoder, which means that we can also scale our decoder and match or even outperform the cascaded models in English to X2. In speech-to-speech comparison, I guess the results are also positive. Again, in speech-to-speech, it's difficult to find baselines that are doing English to X. So we're only doing X to English in this, and we are outperforming the best cascaded model, but by more than 11%. So the cascaded model here, like S2T, you use ASR plus a strong text-to-text translation model, but here you have to add some component that will take that text translation and vocalize it into audio. And for that, we use your TTS, which is an open source TTS model that can work mostly on English and Chinese, I believe. So only tried it on English, and now we can evaluate multiple languages on the source side, but only English on the target size. And here we're outperforming this 3-stage cascaded model, as well as the 2-stage cascaded model, which is usually weaker than the 3-stage cascaded model in X to English on both data sets. So I have it here FLIRs, which covers 100 languages, but only 81 are evaluated here because Whisper only supports 81. And then CPSS, which is a much smaller data set with 21 languages. And we are outperforming, the cascaded models on both of these data sets. The strength, or I guess the strength and the key thing about Seamless in 40 is that it's multilingual, multimodal, and multitask. So it can do all of these tasks with a single model. So when I mentioned, like, for example, Whisper can only do ASR and S2T, whereas here we can do ASR, S2T, S2ST, and text-to-text. Plus, we also evaluate this new task called it's text-to-speech translation. So you can write some text and then you will generate speech in another language. And this one is evaluated 0 shot. So the data I described is only ASR data, S2T data, and S2S data, plus the G2T when I was training NLB. But this task, we don't have any data for it. So the model was never exposed to text-to-speech data, but we can evaluate it 0 shot and get decent performance. Again, there's no baseline to compare against for at least the text-to-speech translation, but for the other tasks, namely the ASR and to text translation, we outperform like strong models that are like specialized in a given task. So for example, NLB is specialized only in text-to-text, and we are outperforming, I guess, on parity with that. And then Whisper Large is a strong model in ASR, and we're outperforming ASR with seamless media large, we're outperforming Whisper ASR, and then MMS, which is also released from Meta maybe a year back, which covers 1,000 languages, and we're slightly behind that in terms of ASR. Especially it depends on what version of MMS you choose. So MMS has this version without a language model on top, and we are better than that. But if you add some language model on top of MMS, then we're slightly behind this version of MMS. So beyond just blue scores, which is looking at the accuracy of the translated data that we have in terms of evaluation, we also evaluate robustness to noise. If you've read Whisper, then a lot of their contributions are about how to make this model robust to noise, especially when you're dealing with speech as inputs. Some slight noise in the inputs, or your microphone is not a good quality microphone, then you end up with very variable results when you run this model on this noisy audio. So to evaluate how robust is our model to noise, we evaluate, I believe here on 4 languages. We have Standard Arabic, Russian, and I believe Spanish, I forgot the other one, French. So we have these 4 languages, and we take some existing data sets with noisy, just some sampled noise, and you add that to your evaluation data, and then you generate. So you can either add noise with some natural noise, some music, some speaking, also people speaking in the background, and you try to evaluate the quality of your model with this noise input. And you can increase the noise and see how the performance of your model will degrade with the addition of more noise. So you can see here as we move from left to right, we're adding more noise, so the quality of the blue scores will also deteriorate. But it depends on how fast does it deteriorate and how are we comparing to other models. So here we're comparing to Whisper Large V2, which is already a good robust model in terms of dealing with noise on the input speech side, and we're seeing that we are much better than Whisper in terms of robustness to noise, either with natural noise or with music. On the right side, I have word error rate. So the lower word error rate, the better. And you can see that the word error rate increases as you add more noise. And particularly with Whisper, if you reach high ratios of noise here, so then the quality of the transcriptions gets way worse. So on average, we are 38% better than Whisper Large V2 in terms of robustness on these 4 languages. The other thing we also evaluate is robustness to speaker variation. So the FLIRS data that I mentioned that we evaluated throughout our work is you have each sentence is uttered by 3 speakers. So you have, let's say one given sentence as input, and you ask 3 people to vocalize that sentence, or pronounce whatever is said in that text. So for each sample, you have 3 speakers. So you can evaluate how our model is dealing with different speakers, given that it's the same content. Because, when you're dealing with translation, it could be a question of maybe I'm saying something that is difficult to translate. It's not about the speaker. But if it's the same content, different speakers, then you can sort of assess how your model deals with this speaker variations. So evaluate variations of the quality of the translation given the speaker, and we are 49% better than Whisper in terms of how we handle different speakers while still getting consistent quality regardless of the speaker. I mentioned that in S2ST, we evaluate also with ASR Blue, but I didn't describe what is ASR Blue. I described Blue, which is, you have text, you can measure some, precision based on engrams, but when you have speech output, how are you measuring the quality of your translation? So for that, ASR Blue is the metric that is used widely in any speech translation paper. And that consists of using an ASR model to transcribe the speech. And once you have this transcription, then you can evaluate using regular Blue, because now you have text, you can evaluate with Blue. So we have this ASR Blue metric, but it's sort of very dependent on the ASR model itself. So in our case, we evaluate ASR Blue, and for the ASR system, we use Whisper. So you can argue that maybe, yes, maybe this will be biased in favor of any Whisper model, because we're using also the Whisper to evaluate at the end. So that's why we proposed Blazor, which is a modality agnostic metric for evaluating speech-to-speech. So it's based on sonar that I described for mining earlier. So instead of, going into the text and then measuring accuracy in the text space, you can directly encode this output speech into a vector, and then you can compare this vector of the reference to the vector of the prediction, and now you can just measure some distance, and the higher the distance, the worse is the translation. So we also released with Seamless Info this metric of Blazor 2. The nice thing about Blazor, because it's based on sonar, it can encode both text and speech. So you can use this same metric for text to text, for speech to text, for text to text, and any multimodal translation from either speech and text to either speech and text. And it's also proven to be like highly correlated with human evaluation, which is the gold standard when you evaluate in like translation models. You run human evaluation and you show the output of your model versus the reference or versus another baseline to human annotators, and that would be like they have the final say on the quality of a given model. So as I mentioned, we released Blazor, but we released everything. So that's why I like working at Fair, because our core value is that everything should be open sourced. So Seamless M40 models are open sourced. We released the inference code and fine tuning recipes, and all of that is using FairSeek too. I don't know if you're familiar with FairSeek, but when I was a PhD student, that was the library I used with FairSeek for any sequence-to-sequence model. I know that now that a lot of people use Hugging Face transformers or Hugging Face datasets, but for me it was FairSeek, and now we're releasing FairSeek 2, which is much lighter version of FairSeek. Also much cleaner than FairSeek in terms of code. And they were also releasing tools to create the mine data I described. So the encoders, all of them are released, plus also my metadata for all the crawl data, that is the sort of the source that we use to mine the data that we call seamless align. So I have here links to the paper, to the blog post. I also have a demo in which you can, translate, you record your speech and translate it into text, and then, translate also into speech, and select a few languages that you can try this model on. Everything is open source in this GitHub repo, and we have a separate repo for FairSeek too. So in terms of next steps, so I mentioned earlier that the North Star goal of our team is enable seamless communication without language barriers. And whenever we're talking about what is the idea, I guess the corresponding corresponding fictional device, it would be like the Babel fish from the Hitchhiker Guide to the Galaxy, where you have this fish that can translate anything that anyone says, even if it's like a new language that you've never seen before, and also it can do it in like streaming online fashion. So the next step for us would be, can we enable streaming in this model? Can we output translation on the go, especially when you're doing speech to speech? So for example, in the case of an international conference, you want to hear the translation while the speaker is still speaking in another language. We also want these models to be expressive, which they're not now. So if you generate speech, it will be like in a sort of not robotic voice, but it depends on what data was used to train the vocoder. So if let's say, it's for Arabic, it's usually like, it will be with some Egyptian accent, and whenever you speak Arabic, it will be in that accent because that's the data that the model saw. And we want to add like expressive components to this model to sort of either, for example, carry the characteristic of the speech input into the speech outputs. And then ultimately putting all of it together, have expressive model that are streamable, but also multilingual and multitask. You want one single model, similar to the Babel fish, that can do all of these tasks at the same time with good quality. So yeah, so that's it for me. If you have any questions, please feel free to ask. We still have a few minutes left.
شكرا مها. دونك en fait les questions غنجاوب عليهم بلي لونغ اللي كانوا مكتوبين بهم.
Ok.
Alors en fait ce qui s'est passé c'est que في الاول وقع شي بوغ دونك البرودكاست ما تافيشاش في فيسبوك. Donc la quantité de viewers était beaucoup moins que la dernière fois à cause de ce bug, mais c'est pas grave. La conférence a été enregistrée, mais il y a pas mal de viewers sur LinkedIn, donc c'est bien. Donc, je pense que les questions sur LinkedIn qui t'affichent au Genève, donc je vais donc bidder.
Mhm.
Yeah, there's a pretty general, maybe too general question. I don't know if many thanks, Maha, for your presentation. We noted that machine learning or AI has included many techniques and practices. My question is about the next steps of AI. This is like extremely general. I don't know if you don't think it's worth answering, we can skip it, but
I
it's
don't
your
know if
call.
it's worth answering or not, but
Oh yeah, sorry, I'm gonna do this.
right. So I know it's general, but like if you attend any of Jan-Lucan's talks or tweets or whatever, he's already speaking of like general intelligence and like what is the next step for reasoning. Because a lot of people will criticize language models, saying it's just next token prediction. We want something more that does more reasoning than that. That I guess for me, like what I because I like the work on the space of multimodal, either translation or anything. Like I want a model that can understand any modality. Like for example, in this even speech translation or translation in general, it could be lip reading, it could be sign languages. For me, it's this inclusion of all these different modalities, mapping them to I don't know some shared space, and you do all of the reasoning in that vectorial space instead of just modalities. Ultimately, modality doesn't matter. Like the idea is basically the same, whether I'm saying it in audio or text or signing it or whatever. Like for me, it's the reasoning in that space that is more, I guess, most interesting. So I can imagine like some assistants like any language model, I guess chat tuned language model that can handle all of these multiple modalities. When you think of Jarvis from Iron Man, like, you can take a lot of inputs, a lot of modalities, and output a lot of modalities connected to a lot of stuff. I think that's like the short term. By short term, I mean 5 years. I think that's doable. So that's for me the next 5 years. I don't know about the rest. Like from 10 years from now, that's beyond, I guess, my expertise at this point.
Okay. If anybody has any further questions, we would gladly take them. Even though I think like most of our viewers in Facebook didn't see the start of the presentation, so they might not have questions. But let's wait like a minute, and if there are no questions, we'd gladly take questions offline as well.
Yeah.
So let's wait for a few seconds, see if anybody has questions. And let's say it doesn't have to be about AI. It could also be about, I don't know, if you want to work at Meta and you want to ask Maha how to do that, you could do that as well. But yeah, feel free. Okay, we have more comments in LinkedIn. Okay, no, just people thanking you for the presentation. Okay, I guess we don't have any questions. So the slides of this presentation are going to be in GitHub.
I'll share the slides, and then
Okay.
you can send them my way, or people can send me the question directly on LinkedIn. Whatever. Okay.
All right, perfect. And if anybody has any questions, I'll gladly take them and forward them to Maha. We could answer them whenever you want. Thank you, everyone. And let's see you again in another conference.
Perfect.